Okay, so good morning, everyone. My name is Handong. I'm glad to be here and to show, one of our recent work along the federated learning strategy. And like the other talks mostly focused on vision, today I'm going to talk, mostly on the NLP field. And I'll share you, some unique challenge we are facing in handling the text data instead of the vision. And naturally, there are a lot of different, differences between. So, before I like to shout out to the collaborators. This is basically, this talk, the content is mostly built on top of our recent work, published in this year, 2020. And this is a collaboration work with a number of folks, Adobe Research, Zhao, Tom, and a number of researchers in Purdue, Hao Yu, Yaqing, and Professor Jinggao. Okay, so this is going to be the outline, and I'll talk about the motivation and especially the use cases we're facing, when we do the, when we try to, build the system for the industry applications, within Adobe. Then I'll talk about the federated knowledge composition, which is specifically designed for the NLP, but I think it can be also extendable to the vision problem as well. Then we'll talk about the experiments and some other thoughts around the future topics we believe is really and the less explored in the current federated learning, field. So, okay, I'll start with the motivation. So I like to use this picture, and it's the GDPR. And maybe many of you are already aware of this term. It's the General Data Protection Regulations, regulation. And, since this comes out and all the companies, is basically can't be more careful about the customer's data, right? And if you're not complying with the GDPR, you've got a very big, expensive check. So Adobe as well, yeah, same. We are very careful about the, customer data privacy. Well, actually, GDPR is just the beginning. It's just the beginning. And this is just, you need to have some very general guidelines, but a lot of companies or customer actually, they have further imposed their requirements, based on the GDPR. I give you an example, right? Some of our customers, they also have, we call it 30 days policy, which means their data flows into the platform, Adobe platform, or either in their, client services. They only have 30 days of the data retention. After the 30 days, the data expire, right? Imagine if you train the federated learning framework, the model on the local server, right? All of a sudden, the data disappear. Then how can you retrain that? This naturally presents another, challenges. If the data evolving, say the new task comes in or the new class, right? The data distribution shift. Then this naturally comes to the forgetting problem, which exists or actually is the continual learning, challenge. So this basically imposes a lot of, unique challenges merit the federal learning and the continual learning. A lot of this kind of challenges I'm gonna, discuss if time permits at the end. But I'll start from the use case, which we are facing at Adobe. Okay, so Adobe is not just famous for the Photoshop or PDF, Acrobat, right? We also have the experience platform, which is like the, digital marketing. We have, a number of customers of different sizes, like the HP, which is the multinational, is famous for its laptop, printer, etc. And the Gartner, maybe you have heard or not heard the. This is about the home furnishing. And headquarters is in Germany, and the Home Depot, right, is also about the home furnishing. So we have tons of data. Their customer data flows into our platform or their local services, even flows in our platform. Actually, they have all their data stored in their tenant account, which means their data is not shared. Is highly speaking. Even though the transmission accuracy, the transmission efficiency is different, right? There's all on our platform. There's not a lot of overhead or a lot of cost, transfer from this disk to another disk is in the same data lake. But the high-level architecture can be still, structured in the FL, framework. It still need to synchronize in our, high-level server. Then we need to redistribute it. The data is not directly shareable. Okay. So let's say I just want to high-level talk about some vision topics since this is the CVPR, right? And we have the images, collected from different customers. It can be, like the second is about the furniture, and the third one, Home Depot is also about the furniture. But each customer, like the second one, Gartner, they're about the home furnishing or the table and the chairs, and they specialize on the tables, which means they have all kinds of, category or subcategory about the tables. Well, Home Depot is more like a department store, right? We have different categories, but in terms of the table or chairs, I would say maybe it's less, diverse. So we believe that if we want to provide a good, services, we want to jointly learn from each client, then it's better capture if you want to do the segmentation, if you want to do the classification, right? And this is a good opportunity to learn across clients and provide the benefits or provide the better services for, for Gartner or Garden or the Home Depot. Okay, and the language, right? And we are a global company, and like the second customer, the Gartner here is most of their customer is in Germany, so their comments is written in German. And it's still about the table review, which I paste here, the Garden and the Home Depot, but in fact, it's about the sentiment analysis, right? The second one basically say the chair is easily broken, is an active one. But if you want to learn across the customer, right, you have two separate models trained on. One is in German, the other one is on the English. You can imagine the same network, you want to synchronize, aggregate their weights, it can be problematic. It's gonna be not smooth. So basically, this is the motivation. I'm going to talk about this, but before that, I'd like to highlight there's also the vision language applications, even the audio we collected. But I would say audio probably is just the minimum, is in the videos. So the vision language application, which we can do, cross-lingual, cross-modal or multimodal product recommendation, right? We can do the VQA, etc. This kind of the vision question applications. Actually, the federated learning can always provide a better solution. You try to learn across different customers and provide a better services. All right, so as I said, I'll focus on the language, which is my expertise, and we are proposing a sort of new ideas. It's called the federated knowledge composition. And to handle this kind of case, I'll show you a multilingual case, right? As a company, we have different languages. I'll show you a very simple idea, example. Is this sentence is only 3 words, right? It's the Peter study Korean. Right, as in English, it's only half, it start from the subject, then the verb, and then the object, right? And this is the syntactic structure, and it has the 3 words, right? And if it is written in Korean, firstly, I cannot say Korean, sorry about that, but this is the example we can understand. And the syntactic structure actually is different. It's subject, then the object, then the verb, right? This is actually happens to a lot of, when it comes to the multilingual cases, it's pretty narrow. It's pretty common. Because of the geolocation, geographical factor, a lot of factors, actually the languages family, there are quite a lot different. So not mention that word vocabulary can be much different. Imagine you train the English and train the Korean and separate the services, and you try to synchronize or aggregate on the server. Directly aggregation actually doesn't really work. All right, and on the right-hand side, there's another, example. I just want to, highlight that say each client in written, is in Korean, and there's another client in English, written English, right? And the aggregation of federated learning, we can still call this as a non-IID, right? A lot of FL paper, they focus on this, but this kind of non-IID is, the domain gap is extremely large. It's not simply a day or night like a domain net, the domain adaptation paper they usually address. So this kind of problem, even though they're semantically the same, or the close actually the same, but in raw data level is totally different. All right, so what do we want to do about this? So this is not the federated learning framework, but I just say it as the decentralized training or distributed training. You cannot directly aggregate on the server side. If you train two separate models, then you aggregate directly, right? But what we want to do this here is we still want the information to be, to be shareable or to be consistent. So as a very intuitive way to solve this, a straightforward is, let's say Peter study English, which happens to in the client I, right? And I get a prediction, say, hey, this is about, say, the text classification task. Then the client one happens to be the, a client in Korea, right? So the model I train on the first client, I also want to have the capability to have the consistent prediction of Peter study Korean. This is a pretty natural idea. Then you have basically all the clients, they have the similar capability. Then on the top of, on the server level, then maybe you can aggregate. Otherwise, it's totally separated. And actually, this exactly describes the idea of knowledge distillation, right? You have two models, right? Distill from the teacher model to the student model, or you can distill back. Here, the concept is the same. You want to, transfer the capability or representation learning capability, between every pair of clients. Yes, so we can definitely do this. If we try to write that more formally, we can write in this form. Forget about the notation, but conceptually, the S represents the token in the sentence. And I'll miss some, but the I here, if we only treat the client I, and we basically, the first term is about the standard classification laws. Here we treated the classification as the task, as the task bed. Then it's basically every sample in the client I, and we want to do the classification. And the second term is just to describe the consistent laws. Every pair of client I and another client, we go through the entire client size, except that here it denotes in M, right? And we pass through two models. One is M client and one is I client, a client. And we want the prediction can be consistent. Here, the prediction function is the F. The consistent is measured by the cross entropy, which is the CE stands for. Right, so basically we want to pass through the same sample into client and get the similar prediction. Well, is in federated learning, this is not allowed, right? You need to share the data. So this is not allowed. We know this. How about this? How about we are not encoding the token, right? Which is the ID. You can directly know what the sentence is. We can encode the embedding. And here I'm saying not the word embedding. The word embedding is the same as the ID. So the word back basically, you know what is the word. I can encode certain layers, not just the base layer. Is some layers in the bird, right? And it is not that easy anymore. But there are tons of research. I won't say not tons, but there are some research they study, like Professor Chen just mentioned, that you can always attack that using adversarial, attacks. You can reverse the gradient and you try to guess the index from the embeddings. So this is still vulnerable. And what we want to do is we still want to share something, I know in standard or the classic federated learning this is maybe not the allowed or encouraged, but we argue that you share not just one sample information, just to share a group of, say, local statistics. Is compare you share the model is still risk, right? The model inversion, and this is something we want to explore. Right, I know a lot of maybe criticism. They say, okay, you still share some statistics, even not the sample wise, even the cluster wise, but you still share something. We agree. But in this paper, we are actually made a theoretical analysis how hard it can be recovered by sharing this information. But before that, let's talk about the case. So for now, let's forget about the first term, which is the standard classification loss. Only see the consistent loss here. And let's try, I'm trying to write in this form. It's more, it's cleaner, right? Basically, you try to capture is for the client I only need to excise all the client in the other client I'm here. And I want the prediction. I want the embedding, which is not the word embedding. It can be any embedding in intermediate representation and their corresponding prediction, right? This is very heavy and this is not safe. And I don't want to share the individual information. I want to share a group level or aggregate or corrupted information. What I do here is we expand, we do the approximation. We not directly share the embedding, but we do the first order Taylor expansion on the point of, basically under the assumption that this function is Lipschitz continuous, right? We can do this. And if we plug this back and to this form, and interestingly, we'll find that this loss function, enforce the consistency is no longer about all the embeddings or all the samples in the other client. In fact, you only need to take the average embedding or the correct information, which you need to evaluate when you do the Taylor expansion, which is the E here, and their corresponding, prediction. And this is actually well studied, when they do the error analysis of the Taylor expansion, and we find the optimal solution, with the corrupted information here actually is just to take the average embedding of the intermediate layer of the samples in the client end. And you need to, you don't need to, transmit all the information, all the embedding to the server, then desynchronize. So you just need to aggregate locally and transmit the average. So what we do here is we make analysis whether this form is easy to to be attacked. And also I'm going to show you that the experiments we do, just apply the adversarial attack, and whether we can retrieve back, given the embedding, then retrieve back the original sentence we got. Basically, is the word token. But let's see this. This, in fact, is not optimal, which is pretty obvious. You basically aggregate all the information in one client and share that, right? You try to do the consistent. Well, what if the information in that client is very diverse, which is commonly happens. So we do one step further, which is also very straightforward. We do the clustering, unsupervised clustering on each client. Then basically we get Q cluster and we share the centroid. And here I want to highlight here is the centroid is the mean of that cluster. It's not like the prototype, some very common or popular concept, the prototype, which is basically is the class represented samples. That is the one sample in that class. Here, the centroid in the k-means means the average in that cluster. So doesn't really affect our previous in the paper our discussion or theoretical analysis. Okay, so overall this is going to be our framework. And on the right top corner is still the synchronized way, the way we communicate. And the bottom here, we see two blocks. Basically, is two models inference and how we do the consistent loss. From client one or another client, we do the clustering, then we get the centroid, which is the mean, then we share to the cluster, then we try to have, firstly share to the cloud, then we redistribute it back, then we can calculate consistent between these two clients. And this is the consistent loss. And the classification loss is just normal. Okay. So before I formally talk about the experiments, I want to quickly highlight the communication cost. In our experiments, multilingual aspect research, we heavily depends on some pre-trained model. Here we are using is the multilingual BERT, which is very hard. It's very large. Is like one model is 110 million parameters, and we definitely, based on that, we need to introduce more parameters. Here in our standard setting, we do the experiments. This is on 10 clusters, and each round we roughly have 10 active clients, and if this is the 10-way classification problem, this is the number of parameters we introduce. So it's still a lot, I agree. So, but in the future work, I'm going to talk about some other directions. How can we further reduce or fundamentally reduce the number of parameters we want to share? But before that, let me talk about the main results first. So we conducted on the 3 standard, NLU tasks, natural language understanding tasks, including the paraphrasing identification, the QA, and the news classification, right? This is only the PI, the paraphrase identification task, the results, and it's 7 classes. And we compare with a number of baselines, including 2 standard, very, classic way, Fed average and the Fed prox, and 2 recent one. One is the moon, one is the Fed mix, which sort of share the similar ideas. They also explore the idea, you do the mixed up on the image level, which naturally you can do that here. You have 2 images and then you can add them together, right? You take the mean in the pixel level. Well, in our cases, we cannot do that. It's the ID as the input, the token, right? Index. So you can always do the word embedding level average. That's what we try to tailor the Fed mix to our scenario, but in fact, you can see it's not working well. And also I need to probably want to highlight our structure. So it's, as I say, is the MBERT as the backbone. And on the top of that, we take the average pooling layer and get 1 representation for 1 sentence or from 1 document. And we append another classification layer, which is the classifier. Then we do the prediction. So we have 2 backbones, try here, or 2 model averaging strategy. One is Fed average is standard. One is the Fed prox, which you want to consider the straggler cases. You want to slowly updating your local model to avoid some, dramatic change. Well, interesting thing is I want to highlight first is Fed mix. As you probably know, that is working extremely well on the images, right? It takes the mixed up strategy and dramatically boosts the performance of the Fed average. Well, in fact, here, as you can see that in the NLU, it doesn't really work. As I say, what we're trying to tailor their methods on here is you cannot directly add on the index level, but you can always do this aggregation in the embedding, word embedding level. But directly do this, the improvements is really marginal. And which suggests, actually, this is not only findings that mix up type of data augmentation is very not straightforwardly working well in NLP field, right? Mix up is working extremely well in the images. But since the nature of natural language is about the token IDs, concrete, discrete, values, and the way how to do the mix up is not very clear. And basically, this is in the federated learning setting, we try to, we see the similar cases. right? And another behavior we see, which is also very interesting here, is the way we aggregate we update the local parameter. One is the Fed average, one is the Fed prox. Fed prox actually is very robust in CFAR, in ImageNet, which in their paper they experiment now, right? But here we see, if you see the average performance is comparable, is nothing really different. And after analysis, we believe this is because the benefits we do is the consistent between these two clients. This kind of knowledge composition actually compensate the defect of Fed average, which is the straggler, or is the faster updating strategy, which is the Fed average originally have. So this is an interesting observation, which demonstrate sort of our this kind of consistency enforcement can prevent some over aggressive updating, the drawback. Then we have some standard study on, since we do the clustering, we want to capture the fine-grained information on each client, the more diverse patterns. And this is basically shows that we can do this. This is also performed on the paraphrase identification task. And for each case, you can see on different strategy. Oh, by the way, the last layer basically means we have the loss and we only fine tune on the classification layer. And the all layers, which means we can use that loss to fine tune the entire network, which here it means the Ambert structure, right? And we can see the consistent improvements. Right, then it comes to a very interesting experiments we conduct, is we try to understand, okay, I share the center, I share the mean of that cluster basically to another client, even though we share on top of the cloud, right, the global server. But can we say there's a malicious user and we share the embedding? Can they use the embedding to guess or to attack it back to understand what's the original data which my local server have, right? So this is one example we conduct, with one experiment we conduct, a sample sentence we use for this experiments of one cluster, right? Basically, this is one cluster contain sample example sentence like this, and we share the embedding, the average embedding of these sentences. And this is the results. We try to use the one of the recent adversarial attack strategy, which is proposed here, information leakage in the embedding model, since we share the embedding, right? And this work, basically what it does is they try to optimize the strategy from the given embedding. They try to find the mapping to the index. They try to optimize this. And here the x-axis represents the number of candidates, which means that we give the embedding, right? And you try to guess the corresponding token ID, the index, as long as that index in the top 10, 20, 50, then we count it right. Basically, it's the hit ratio at n. And we find that the Fed average both layer model or fine tune the older network, which is the O layers, the red line. And it's not easy. The 10 means the retrieve ID is in the top 10 list of one token here. In the sentence, it can be 128 tokens, right? If one token, you can only get the 1 out of 10, which is you not get it correct. The hit ratio at 10 actually is both cases is 0. For a sentence of 10 tokens, then the probability to get exact the same token actually is 10, is this number probability to the power of 10, right? This is just a one token example. And especially we find that Fed average, if we want to fine tune the older network, is more robust. And up to the number of candidates up to 50, there's no, empirically find there's no way you can basically, retrieve back or try to guess what exactly this token is, given the average embedding of that cluster. So yeah, basically it showed that even though you use the recent proposed attacking methods and sharing the group of local statistics, not the raw data, is still imperfectly hard to to reverse back. And also in the paper we have some theoretical analysis, try to give a bound, how hard you can recover the original information, given this intermediate average embedding. All right, and we also conduct some a standard analysis on, for example, this is the epoch of local updating, and I'm not going to talk about the detail, but this is the active clients, and we find that the more clients in each round are involved, and more stable or better accuracy or performance you can get. And this is pretty standard, and you can see the similar behavior in the Fed average and Fed prox. This is nothing new. And I would like to spend some time on the future work which we are facing in the reality, right? And the first one, the communication cost. In the NLP fields, we have a lot of foundation models in the image as well, VIT, right? And the clip, which is or DALL-E, is extremely large, right? Clip is is more, on average, it's more than 100 million number of parameters. It's very not efficient, and sometimes it is prohibitively expensive to transmit all the parameters to the server, then synchronize back. And NLP as well, but we can always leverage the pre-trained model, and there's another route of or direction of work which you don't need to fine-tune the entire data, even though sometimes it works well, especially when you have not limited number of samples. You can fine-tune on more data. Then in some cases, when you don't really have a lot of data, then prompt tuning or adapter, which allow you to learn additional few number of, a small number of parameters tailored to the downstream application or tailored to your local data distribution. And this is very parameter efficient or data efficient as well. In this case, as a prompt tuning, as an example, there are a bunch of paper already in this field, and you don't need to share the base or the foundation model anymore, right? No matter it's on the global in each client, it's the same. You just prepend some prefixed prompt token. Or in the adapter, you just inject several layers in between the transformer, then you have a bottleneck network. And that's the parameter you care. That's the parameter you want to learn across different client, right? And provide better services. And in that scenario, you don't need to share 100 million, 110 million parameter. Only, prompt is like, the basic model is like the 0.001 level of parameter, which is very parameter efficient. That save a lot of bandwidth. And this is an interesting direction. And but so far I don't really see any paper working on this domain. Extend the prompt learning or adapter learning in the federal learning, which care the communication a lot. Professor Chen also talked about the lottery tickets. You only share the mask, right? That's another strategy. You don't need to share the entire weights. Mask is binary, right? You can compress everything in the very condensed, memory, then you share that. Actually, this is another strategy to do this. Okay, and I share one paper, which is just highlights how the prompt tuning works. Another way is, as I said, GDPR is general guidance. A lot of customers, they have their own enforcement, their own regulations. And I talk about the 30 days data retention policy, which means some customer only wants their data reside on our local data server, data lake, for 30 days. And after 30 days, the data gone, disappear, right? And if the data, this is the data-wise continual learning setting. If the data involves new class, new task, or task incremental, you need to learn on the local server. You need to understand the new information, knowledge, but you don't want to lose the old knowledge, right? And how you can prevent the forgetting in the scenario of federated learning. This is add another layer of challenge. And I don't either see this kind of work including NLP or computer vision fields, but this is definitely something worth investigating more. And this is we see in the practical use cases. And this is, I show that there's actually some papers starting looking at this general topic, but they don't really consider about the data free or data retention, 30 days data retention policy. They need the buffer at least to host or to retain the data from the time 0 to the current stage, so that they can do the data replay, they can without losing informations. And again, I mean, since you can learn across different customers, you losing some information data samples at your client customer, maybe you can have something, happily to have something in different client, right? This could be possible. How you leverage this kind of information and try to design a framework, considering these cases could be another direction. I just want to shout it out. And another directions is the distribution shift. And they're starting some, I've seen some works, they start considering the domain adaptation or domain shift scenario. Non-IID naturally it belongs to the data distribution shift or different scenario. But most of this work is they consider the covariance shift, right? They are not considering the label shift, which means each client, their data, the class of their care, the class of annotation is different. This is very common. And I can tell you one case, this client, they at this moment say the NER, another example in the natural language processing, they only consider about this type of entity that I do a lot of annotations, or actually annotator at this moment are only familiar with this kind of annotations, right? I do extensively on this kind of annotation. And for the other annotations, say the person, maybe I just do a few. Another client, actually, they are very strong to annotate the person, but not the organizations, right? So, or sometimes no organization. So they actually doesn't really mark the organization as annotator or anything. And in fact, this is the case of label shift. The two models to train, one considered person, one is not, but that particular token doesn't mean it's not contain person. It's just the person, it's just the annotator don't explicitly label that out. So the problem comes. So you want to consider this case. And in the NLP field, we don't really have this kind of work for now, but I'll say this kind of thing is also exists not in the federated learning setting. It can be appear in the open, open set domain adaptation problem. It can be happens in the task incremental learning problem, but in the federated learning setting is have this unique challenge, which we plan, but we don't really start investigating this direction yet. And on the right side is an existing paper, recent paper, which they start, considering the domain adaptation, different angles, or the day and night, it's not just the data distribution, the standard non-IID scenario, which, most federated learning paper they consider. Okay, and above this three, actually, what we propose is orthogonal to other, privacy preserving strategy, like say the differential privacy. And of course, it's a good direction we apply the differential privacy DP strategy and to our, framework and see whether we can further improve the privacy concerns. And this is the most reference I use. With that, I would like to conclude my talk, and thank you for your attention. I'd like to take the questions.
Thanks, Dr. for the great talk. Yeah, you can ask because on the Zoom. I see. Yeah, thanks for the great talk. Actually, I want to ask one question regarding the one of the future directions you shared. So for the adapter-based method, what I understand is although it is very data efficient and parameter efficient, you only need to study learn a few parameters, but actually you need to do the forward and store all the features or parameters or gradient during the forward and backward. So do you have any insights of how the adapter is can be applied in the federated learning and solve this kind of concerns on potential bottleneck of using adapter together with federated learning? Yeah, thanks. Yeah.
Okay, this is a good question. So, yeah, I mean, the adapter or the prompt tuning still need, even though it's data efficient, you still need a sample, a small amount of sample to do the forward pass and backward pass. But compared to the standard fine tune, or I would say compared to the standard, federated learning, you train the entire network from scratch, you leverage the pre-trained large language model is already very data efficient. And this is already a very good data efficient strategy. You can only use a small portion of sample, which in your domain, fit your local, task or local data distribution. And then you share the small number of parameter either in the prompt, soft prompt is the parameter you learn, or the adapter, which is the bottleneck structure you learn, and you try to aggregate on that level. I would say, to me, this is already very data efficient. If you look at the paper in the prompt tuning or in the adapter, this is way more economic than the Euro. I guess without other special treatment, say there are something we can further share, or either layer-wise sharing or some sharing, it's very hard to further, reduce the data. Yeah.
Thanks so much for the answering. Yeah, I'm also looking at this problem, and actually, I think this is actually quite good because the better can reduce the parameter or data or the energy you need on the edge device to update the model, and the federated learning can further the benefit of every edge device.
Thank you for your question.
Thank you for the talk. I did arrive a bit late, so I mean, I actually surprised that Adobe is interested in this kind of application. My question is regarding like learning, federated learning in the context of heterogeneous devices.
Okay.
And especially mobile-aware devices,
okay,
on the edge devices. Because I mean, so far, like most of the research is still driven by CIFAR kind of ally stock. So I was wondering, like, what's your opinion about that? And if you are aware, also like put it probably the answer in the context of the new work in self-supervision with federated learning.
What's your second question again?
Self-supervision in the context of federated learning, because there is a recent archive paper like cross-silo business.
Okay.
I mean, if you don't know, it's okay.
Okay, I see. Okay, cool. Yeah, the first question I think is about the on-device, right? The hardware aware. You know, at Adobe, we do face this kind of issue, you know, this kind of unique challenge. Either way, we in this paper, we mostly, or in our majority work, we most likely consider the case that the data flows in our data lake. They enter different account, and which means we have a supercomputer to support it at the end. In the back end, we don't really face any, you know, some computing issues. But I know the naturally federated learning, it can be applied to the edge, can be applied to, say, even the laptop or a mobile phone. And in that scenario, you know, in the separate work we are doing is not this work is we try to do the hardware aware kind of distributed, I won't say distributed training, but hardware aware domain adaptation, and try to synchronize the information or the knowledge from one is like cloud, is very heavy, big model, and try to transfer the knowledge to the on-device, which is the laptop. We have the Photoshop, which is the laptop version, right? And we want the detection or the super resolution efficient, you know, is more efficient. And in the federated learning, of course, is going to be beneficial if we can, one is on the laptop, one is on the server, you know, they can communicate or they can learn from each other. Then I would say this could be our natural next step. And we try to, you know, go one step further, and not just the cloud kind of client, but also the laptop on device kind of client. And, but I think the natural challenge is, you know, the model size first is different. Laptop version or the app version is way smaller than the cloud, right? One is on the GPU clusters, one is on some local GPU, right? And how we can share the model, and which is the model size is not the same. How can we share the information across different models? This is naturally a good direction, which current, you know, federated learning, they don't really consider this challenge. But I guess this is a really good question. Even, you know, we don't really consider this, but this could be a natural next step. And the second one, yeah, like I said, self-supervised learning is very popular and powerful right now. But I would probably want to argue one thing is, you know, federated learning here, one very useful application is the number of label sample or number of samples in the client is not very sufficient. Otherwise, you can train a separate model on a local machine, right? On the local client. But always you can argue that, you know, some client, they have abundant information more than the other, and you want to learn across that. And I would say Moon is kind of try to apply the contrast learning, and you can always apply other strategy, you know, data augmentation as example, self-supervised between the weak and strong, you know, augmented samples. That's another route, I would say. But in terms of the application, what we are seeing is more, you know, you try to from more abundant or richer data, and try to help the, you know, the low resources cases. And most likely, yeah, the data is not that sufficient to do the self-supervised learning. Yeah. Just do the follow-up.
Sorry, I don't know. I shouldn't be a discussion. So, I mean, that's an interesting point, the last bit that you raised. And from that, I mean, this is a question kind of like it's nagging me, like with federated learning, like, for example, I mean, like, how do we quantize, I mean, like, or how do we summarize knowledge? Because at the end of the day, you just say, like, I mean, we have one client that has an important data, and we have the generic model, and each client will have an enriched version of our server model associated with the data that it's there. So there is like the reminiscence that, okay, we have a model with some knowledge, and we have like an enriched model, hopefully an enriched, okay, or like model prime.
Yeah.
and it comes like, I mean, like, how do we, the knowledge, I mean, no,
I know.
not aggregate, not aggregation, because aggregation, like, it happens, right? I mean, it's like, how do we, like, for example, say, like, I mean, it's like, have you play, like, for example, soccer, like in video games? You put like, oh, this player, high speed, like shoot a lot, whatever, stamina. I mean, the enriched model, I mean, will have like its own mapping, no? Basically, I mean, some characterization of the knowledge, right?
Yeah, thank you for your question. I see you're probably a fan of soccer. You wear the soccer G's. Yeah. Yeah, I would say this is definitely a challenge in the federal learning. You know, federal learning naturally have a lot of characters. You know, each client, their business can be can be different, right? Like I used the example, the Home Depot is more department, and the gardener is just specialized from home furniture. I'll say this kind of challenge is not unique for the federal learning. It's just federal learning can be even harder. One, there are common strategies can solve the mixture of expert, right? And you can also do the modular network. For one specific set of information, you can learn one module, and you try to selectively synchronize the information. I think high level speaking, all that kind of type of work can be applied here. But again, I mean, in terms of the federal learning scenario, this kind of challenge can be more severe, or this kind of limitation can be harder. Yeah. Okay, cool.
Okay, all right. Thank you so much for the great talk. So I think we learned a lot, especially from the industry, because you have a lot of very real problems. So that's why I also make federal learning very interesting, because we have so many, different type of scenarios we have to deal with, right? We have a lot of settings we can, experiment with.